So patterning parameters, patterning control. Let's now see the last important parameter that we can change when optimizing the patterning for our TSPL, which is the pixel size or pixel distance. So starting from this image here, we can really understand what this pixel size or pixel distance means. So if we have if we pattern two pixels that are very close to one another, then these two pixels will merge. Then if we keep on increasing this distance, the pixel will not be forming a continuous line. So of course, when we want to do standard patterns with the nanophraser, we want a continuous line. So we keep dimension of pixels to a reasonable reasonable for our tool, which is around 20 nanometers, and reasonable also to the dimension of our tips at their apex. But we can see what happens when we increase the pixel size in terms of efficiency of writing and also to some extreme cases. So let's now go to the nanophraser software to show you the effect of the pixel size. I would like to use the write arbitrary function. We could also use a geometry, but it just takes a little bit longer. From a geometry tab, every time we import a design, we can change the pixel size in X and Y. So we can import a design and add it as new design with different pixel sizes on X and Y. But using the write arbitrary function, we can directly change them here without importing a new geometry every time. So it's quite useful, I would say. So let's see. Here we have this small 3x3 area, which we pattern at a depth of 20 nanometers with a pixel size of 20 nanometers, and we see that we have 100 by 50 pixel in X and Y. So if we start patterning now with a Kalman feedback, I don't think we have enough data to effectively pattern with the feedback, but let's see. Now we're using a standard pixel size. It's quite a fast pattern, around 49 seconds. So yeah, we see that we are reducing a little bit the force. Initially it was too high. Just to have an idea, I'm using now a pixel time of 25 microseconds, and I changed the force pulse to 2 microseconds. So it's not, I would say, the standard initial value of 5 microseconds. We see that in the analysis, we use a force of 3.5 to pattern at a decent depth of around, let's double check again, of around 20 nanometers. So why not, let's, instead of using this 4 whatever, we use a value of force of 3.5, which will allow us to pattern at a decent depth. So we remove the feedback now, and we will always pattern with this force. So we see that we have a continuous pattern. It's important to mention that after we do the writing, we also do a reading, and in order to define the reading parameters, we have what we call the upsampling factor. So along X, we have the upsampling factor of 1, which means that we read in the same way we write in terms of pixels, but along Y, we have an upsampling factor of 2. So in this case, we have the pixels that are twice as dense along Y. Let's increase this value so that if we increase the dimension of the pixels, we don't lose in resolution. Let's say, and we are able to see more, we're able to see actually better with high resolution what we're doing with our nanofreezer. So let's put high values of, say, 5 and 5. And let's try now to pattern with an increased pixel size. So let's put 60, for example. We see that we have a reduced number of pixels, so we increase the pixel size by 3 times. The number of pixels decreased by 3 times because this is a fixed geometry, so fixed dimensions. We reduce the number. We increase the number. We increase the dimension of the pixel. This leads to a reduction of the number of pixels. If we are importing a geometry, which is a PNG, as explained also in another video. In this case, we have some image settings which are not really nice. For importing a PNG, when we are changing the number of pixels, the dimension of pixels, the number of pixels will always remain the same. So let's see what's going on here. First of all, we see that we are not patterning as deep, and we see that this line seems not that continuous. Actually, it is continuous, but it's not really nice. Let's put it this way. So the pixel starts getting quite far away from one another. We can see that the adhesion length of our tip is quite small. So we're dealing with a sharp tip. So if we keep on increasing the dimension of the pixel, we will be able to see even more in detail what's happening on our patterning. So let's now put 100 nanometers. What we expect is an even larger separation between the pixels. We have an upsampling of 5 and 5, so we will read with a pixel size of 20 on X and Y now. Since the tip has a finite dimension, what we expect to see is that as we keep on increasing the pixel size, then we will have a separation between the pixels. Now we were able to see a kind of a separation between the pixels, but not really. Here it's still not well separated, but we already start seeing it, so that the pixels are not really merging with one another. So the distance between these two indentation, and every indentation should be exactly the pixel size. So this is around 1.35, and this is 1.25, and this is 1.25, and this is 1.15. So this is exactly the pixel size that we are changing in the writing arbitrary function. So we expect that if we keep on increasing it, we will reduce the number of pixels and make them more and more separated. Let's put 200. I only have 15 by 15 array. What you can see is also by increasing the pixel size, we also increasing the range of the scan region because we are increasing the linear speed of patterning, because we're and so this leads to a larger acceleration region needed and deceleration region needed. So let's pattern now and see the results. So patterning should be quite fast, only 30 seconds. It's very few lines, but you can see very well that now we have a very nice separations of the pixels, and now the distance has increased, so it's 200 nanometers between each pixel. To make it even more visible, we can maybe increase the force a little bit. Let's put to maybe 5.5, increase by 2 volts, so that we can make slightly deeper holes. We can also put this to 350. We can also change it, change the dimensions, so we can make it 350, say 250 and 500 on Y. Actually, this is too much. We can put 350 without locking the aspect ratio, and 200. And we pattern. And also increase for an even higher resolution of the reading. We can put this to even 50. Maximum, I think it's 10. So let's put. Let's see. The maximum value that we can put here is 10. So let's put 10 as a sampling factor. And let's start. So we will see that now the pixels will be differently separated on X and Y, because we have changed the dimension of the pixels on the different axes. And still have a very fast pattern. So you see now the distance in Y is larger. We have more clear indentation, so we will see that the distance on Y is around, so this is minus 0.3, and this is around 0.2, sorry, minus 0.13. So this is around 350 nanometers. Well, if we go in x-axis, here we have a distance between the pixel, which is 200 nanometers, and in this case we check again, we put 250 and 350. So how to play around with it? Well, this is a parameter that is not often changed, but if you put the pixel closer to one another, you can increase the efficiency of writing, or you can remove more material more efficiently. If we decrease the distance, if you increase the pixel size, then you will lose a little bit of efficiency. So you can play around in this sense. And I also wanted to visually see visually have an idea of what happens when we increase the pixel size and what actually means pixel size. So it's every indentation that we make with the nanofraser tip. I mean the tip of the cantilever. And this technique is also sometimes used to write array of dots. So if you want to write array of dots even at high resolution, you can do it at high speed, because of course you see how fast it is to pattern quite a large field. You can also make a larger field. You see 20 by 20 only takes 1 minute. And let's just have a look of how big of a field we can make and how short it takes. You can also increase dimension. Say put one. Probably one micron is too much for our software. Put 500 and 500 now. And we see that we have two fields now. We can increase the pixel time so that we avoid the splitting of the field. See, now we have only have one field, and it takes 1 minute and 44 seconds to make an array of holes with this spacing. So I think it's a very efficient way, a very efficient trick to do, and it's also nice to see the pixel dimensions that actually match with the data that the values that we input from the Nanofraser software. So let's have just a quick look of this pattern of array of holes. I see it's quite nice, and maybe can have a look. We can also increase a little bit the temperature to create different depths and really play around. Now patterning much deeper with increased temperature. We're making very, very small indentation if we reduce the temperature. So these are kind of typical depths that we have for high resolution patterning, so below 10 nanometers indentation. So I hope this was it's already quite a long but interesting video for you to understand the pixel size or distance, how to play around with it, and what it means to play around with it. So yeah, this is the last video of the main patterning control parameters. I hope this helped you in understanding better how to play with the Nanofraser parameters to optimize your patterns and what each parameter means practically when we use a Nanofraser.